Tonight we're going to travel to the edge of everything we've ever known, and then keep going. For as long as human beings have existed, we have looked up at the night sky and felt the same thing. Not just wonder, not just curiosity. Something older than that. Something closer to longing. The stars have always seemed to be calling us, quietly, patiently, across distances so vast that our minds genuinely cannot hold them. And for almost all of human history, the honest answer to the question of whether we could ever actually reach one of those stars was simple and devastating. No, never. The gulf between us and even our nearest stellar neighbour is so incomprehensibly large that every spacecraft we have ever launched, every rocket we have ever built, every engine we have ever designed, none of them would arrive. Not in a lifetime, not in 100 lifetimes. By the time our fastest probe reached Alpha Centauri, the civilization that built it would be long gone, buried under thousands of years of history. The stars were beautiful, and they were permanently, brutally out of reach. But here is the thing most people don't realize. Something changed. Quietly, almost without fanfare, a small group of scientists and engineers began working on an idea so audacious, so strange, so deceptively simple, that when it was announced to the world, even the people who understood physics had to stop and read it twice. An idea that does not involve massive rockets, or nuclear engines, or generation ships carrying thousands of sleeping passengers across the void. An idea that uses something we already have, something that travels at the one speed the universe actually permits, and if the math holds, if the engineering can be solved, it could send a probe to another star system within the lifetime of a person alive today. By the end of tonight, you're going to understand exactly why this might be the most important project in the history of our species, what stands between us and the stars, and why the answer to the oldest question we have ever asked, are we alone out there, may finally be within reach. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is a memory that almost every human being shares. You are young and it is night, and someone takes you outside and points up. Maybe it is a parent, maybe a teacher, maybe you found your way there alone, drawn by something you could not name, and you look up at the sky, and for the first time you really see it. Not just a dark ceiling with light scattered across it, but something else. Something that goes back and back and back in a way that makes the ground feel less solid beneath your feet. You felt it then, even if you had no words for it. That vertigo, that pull, that ancient aching sense that somewhere out there something is waiting. We have always felt it. Every civilization that has ever existed on this planet has looked up at the stars and told stories about them. The ancient Egyptians mapped them and built monuments aligned to their rising. The Greeks named them and wove them into myths that have survived 3,000 years. The Polynesian navigators read them like a language, sailing thousands of miles across open ocean guided by nothing but starlight and memory. Indigenous peoples on every continent developed rich, detailed knowledge of the night sky that was inseparable from their understanding of time, of seasons, of life itself. The stars were not decoration. They were a compass, a calendar, a cosmology. They were the frame inside which human beings understood who they were and where they belonged. But there has always been a second layer to that longing, something beneath the navigation and the mythology, something more personal and more impossible. Not just the desire to understand the stars, but to reach them, to cross the dark between here and there, to stand somehow, somewhere other than Earth, and look back at the pale, blue point of light that is home. That dream is older than writing. It has lived in our chests for as long as we have been capable of imagining things that do not yet exist. And for almost the entire span of human history, it has been treated as exactly that. A dream, beautiful, permanent, and completely out of reach. Here is the thing most people don't realize about that dream. It never actually died. Even when science made clear just how terrifying the distances were, even when physicists explained with calm precision that the nearest star was so far away that light itself takes 4 years to cross the gap, even then, the dream did not go quiet. It simply went underground. It moved from temples and mythology into engineering labs and theoretical physics departments, and the imaginations of writers who built entire futures around the possibility. It became the engine of science fiction, yes, but it also became the quiet obsession of real scientists who refused to accept that the universe had placed something so close and so utterly beyond us without leaving some kind of door. And then, something happened. Something that most people missed, because it was announced not with fireworks or a presidential speech or a moment of collective global attention, but with a press conference in New York City in April of 2016. A Russian billionaire named Yuri Milner stood at a podium alongside Stephen Hawking, one of the most recognizable scientific minds of the 20th century, and they said something that should have stopped the world. They said that within the next generation, it might be possible to send a spacecraft to Alpha Centauri, not in 70,000 years, not in 1,000 years, within roughly 20 years of travel time, within a human lifetime. The craft would not be large, it would not carry passengers, but it would cross interstellar space and it would arrive, and the name of the project was Breakthrough Starshot. I want you to sit with that for a moment, because I think we often hear announcements like this and let them wash over us without truly feeling their weight. We are not talking about a faster rocket. We are not talking about an improvement on existing technology. We are talking about a genuine, funded, scientifically grounded proposal to send a human-made object to another star system within the lifetime of people who are alive right now. Children who are in school today might be in their 40s or 50s when the data from that mission begins arriving back on Earth. That is not science fiction. That is a project with a budget, with research teams, with engineering problems being actively solved in university labs around the world as you listen to this. But I also want to be honest with you because honesty is part of what makes this story so extraordinary. The obstacles are real. The engineering challenges are not small. There are problems involved in this mission that have never been solved before. Problems that require breakthroughs in material science, in laser physics, in miniaturized computing, in communication technology. There are moments when you look at the full picture of what Breakthrough Starshot requires, and you feel the weight of it, the sheer audacity of what is being proposed, and there is something almost terrifying about the scale of ambition involved, because we are talking about a civilization deciding collectively to do something that none of the people who design it will live to see completed. The engineers who solve the hardest problems may never know if their solutions worked. The scientists who launch the mission may be long gone before the probe reaches its destination. And yet, that is not a reason to turn away. If anything, it is a reason to lean closer. Because what tonight is really about is not just the technology, as remarkable as that technology is. It is about something deeper. It is about what it means to be the kind of creature that looks at a 4.24 light-year gap between itself and the nearest star and says, quietly, stubbornly, almost defiantly, we are going to try. Tonight, we are going to walk through every piece of this, from the staggering distances involved to the physics of the proposed solution to the world that might be waiting on the other side. We are going to look honestly at what stands in the way and at why the people working on this believe the obstacles can be overcome, and we're going to end somewhere that I think you will find genuinely moving. Because this story, at its heart, is not really about spacecraft. It is about the oldest, most persistent dream our species has ever had. And for the first time in all of human history, that dream has an engineering team. Let's start with the name, because the name itself is almost cruel in its gentleness. Alpha Centauri. It sounds close. It sounds like a destination you could plot on a map, book a ticket to, arrive at with luggage and a sense of accomplishment. In the night sky, if you are in the southern hemisphere, you can see it with the naked eye. It is one of the brightest points of light visible from Earth, a warm golden glow sitting near the Southern Cross, patient and steady and deceptively familiar. For centuries, sailors used it to navigate. Astronomers have known it as our nearest stellar neighbour for well over 100 years, and that word, neighbour, is the problem. Because what we mean when we say neighbour in cosmic terms is something that would shatter every intuition you have about distance, about space, and about what it actually means to travel somewhere. The Alpha Centauri system is actually a triple star system. There are 3 stars bound together by gravity, orbiting one another in a slow gravitational dance that has been going on for billions of years. 2 of them, Alpha Centauri A and Alpha Centauri B, are relatively similar to our own Sun. They orbit each other closely, taking about 80 years to complete a single orbit around their shared centre of gravity. The third star, the one that matters most for our story tonight, is called Proxima Centauri. It is a small, dim red dwarf star, and it holds the title of closest known star to our solar system. Proxima Centauri sits at a distance of 4.24 light-years from Earth. That sentence sounds simple. It is not simple. It is, in fact, one of the most disorienting facts in all of science. A light-year is the distance that light travels in a single year, and light, as you may know, travels at roughly 186,000 miles per second. Every second, light moves a distance that would take you about 2.5 hours to drive at highway speed. In 1 minute, light travels 11 million miles. In 1 hour, it covers nearly 670 million miles. In a single day, light travels about 16 billion miles, and in a full year, light crosses approximately 5.9 trillion miles. That is 5.9 followed by 12 zeros. Now take that number and multiply it by 4.24. That is the distance between you and Proxima Centauri, roughly 25 trillion miles, a number so large that it genuinely stops functioning as a number and becomes something closer to a symbol for incomprehensibility. Let me try to make this real for you, because raw numbers at this scale tend to slide off the mind without leaving a mark. Imagine you decided to drive to Proxima Centauri in a car, a normal car, travelling at 60 miles per hour, never stopping for fuel or sleep or food, just driving, endlessly, through the void. How long would that take? The answer is approximately 48 billion years. To put that in perspective, the universe itself is only about 13.8 billion years old. You would need to make that drive more than 3 times over, in a universe that has not yet existed long enough to contain you, just to cover the distance to our nearest neighbour. That is not a metaphor for how far away it is. That is literally how far away it is. Now let's try it with something that actually moves fast. The International Space Station orbits Earth at roughly 17,500 miles per hour. That is about 5 miles every second, fast enough to circle the entire planet in about 90 minutes. It feels unimaginably quick when you watch it pass overhead in the night sky. At that speed, aimed directly at Proxima Centauri, the International Space Station would arrive in approximately 165,000 years. To give that number texture, 165,000 years ago, modern humans had only recently spread out of Africa. Cave paintings did not yet exist. Agriculture would not be invented for another 150,000 years. Every civilization, every empire, every war, every discovery, every human life ever lived since then would fit inside the travel time of a spacecraft moving at the speed of the International Space Station toward our nearest neighbour. This is why the distance to Alpha Centauri is genuinely terrifying, in a way that is easy to intellectually accept but almost impossible to emotionally absorb. We live in a solar system that already feels enormous. The distance from Earth to the Moon is about 239,000 miles, far enough that the Apollo missions took 3 days each way. The distance from Earth to Mars at its closest approach is around 33 million miles. The distance from Earth to the outer edge of our solar system, roughly where the Voyager probes now travel, is measured in billions of miles. And yet all of that, the entire span of everything we have ever explored, every place any human spacecraft has ever reached, represents a vanishingly small fraction of the distance to Proxima Centauri. If you shrunk the distance to Alpha Centauri down to the length of a football field, our entire solar system would fit inside the first half-inch near one end zone. Everything we have ever touched, explored, or reached with a machine would be contained in a space smaller than your fingernail. And here is what makes this more than just a math problem. Here is what gives this distance its particular emotional weight. Proxima Centauri is the closest star. It is our nearest neighbour in a galaxy that contains somewhere between 100 billion and 400 billion stars. The Milky Way itself stretches roughly 100,000 light-years from one end to the other. Beyond our galaxy, there are estimated to be somewhere around 2 trillion other galaxies in the observable universe, each of them containing hundreds of billions of stars of their own. The nearest of those other galaxies, the Andromeda Galaxy, sits about 2.5 million light-years away. The distance to Proxima Centauri, as staggering as it is, represents the absolute minimum unit of interstellar travel. It is the very first step. And even that first step, even the most conservative, nearest possible destination, is 25 trillion miles away. I want you to hold both of those things in your mind at once, because the tension between them is exactly where tonight's story lives. The distance is almost incomprehensibly vast, and yet, for the first time in human history, there is a credible, funded, scientifically serious proposal to cross it. Not in thousands of years, not in an era so remote it might as well be mythology, but within a human lifetime. The abyss between us and Alpha Centauri has not shrunk. The physics has not changed, the miles are still the miles. What has changed is what we think we can do about them. And to understand how, we first need to understand exactly how fast we're capable of going right now, and why, for most of human history, that has never come close to being enough. There is something deeply moving about the Voyager probes. I want to start there, because they represent something extraordinary about the human spirit, and because their story is essential to understanding just how far we have come, and just how far we still have to go. Voyager 1 and Voyager 2 were launched in 1977, within weeks of each other, on a mission originally designed to last 5 years and study the outer planets of our solar system. 47 years later, both probes are still operational, both are still sending data back to Earth, and Voyager 1, as of right now, is the most distant human-made object in the history of our civilization. It has travelled farther from Earth than anything we have ever built, and when you look at where it is in the context of interstellar space, the result is quietly devastating. Voyager 1 is currently somewhere around 14 billion miles from the Sun. That number sounds enormous, and in human terms it is. But in interstellar terms, it is almost nothing. 14 billion miles is roughly 0.00025 light years. The distance to Proxima Centauri is 4.24 light years. That means Voyager 1, after 47 years of continuous travel through the solar system and beyond, has covered approximately 1/16,000th of the distance to our nearest neighbouring star. If the journey to Alpha Centauri were a marathon, Voyager 1 would have completed roughly the first 8 feet, and it is moving at about 38,000 miles per hour, which is faster than almost any other object humanity has ever launched. At that speed, Voyager 1 would reach the vicinity of Proxima Centauri in approximately 73,000 years. Let that settle for a moment. 73,000 years. At the speed of our fastest currently operational spacecraft, a spacecraft that has already been travelling for nearly half a century. 73,000 years from now, human civilization might not exist in any form we would recognise. The continents will have shifted, ice ages will have come and gone, the sun itself will have aged noticeably. And yet that is the timeline we are working with when we talk about reaching another star using the technology that took us to the outer planets of our solar system. It is not a gap in capability. It is a categorical difference in the scale of the problem. But Voyager is not the fastest probe we have ever built. Let me walk you through the full picture, because it is important to understand the ceiling of our current capability before we talk about how Breakthrough Starshot proposes to shatter it. New Horizons, the probe that gave us our first close-up images of Pluto in 2015, travels at about 36,000 miles per hour, slightly slower than Voyager, and on a trajectory that would take it tens of thousands of years to cover interstellar distances. Then there is the Parker Solar Probe, launched in 2018 to study our Sun up close. The Parker Solar Probe holds the record for the fastest speed ever achieved by a human-made object. At its closest approach to the Sun, where it uses the Sun's gravity to whip itself into extraordinary velocity, the Parker Solar Probe reaches speeds of up to 430,000 miles per hour. That is roughly 120 miles every single second. It is the fastest thing we have ever built, and even the Parker Solar Probe, travelling at 430,000 miles per hour, would take approximately 6,900 years to reach Proxima Centauri. 6,900 years. Written down, that number looks almost manageable compared to 73,000. But consider what it actually means. 6,900 years ago, the pyramids of Giza had not yet been built. Writing had only just been invented. Bronze Age civilizations were emerging for the first time around the Mediterranean. Every empire, every religion, every language, every war, every scientific discovery, every technological revolution from the invention of the wheel to the invention of the computer would fit inside the travel time of our fastest spacecraft aimed at the nearest star. The entire recorded history of humanity is shorter than the journey. Here is what this tells us, and it is important to say it clearly rather than let it hide behind the numbers. The problem with reaching another star is not that we haven't tried hard enough, or spent enough money, or built big enough rockets. The problem is fundamental. It is a problem of physics meeting geometry. The distances between stars are so vast, and the speeds achievable by conventional chemical or even nuclear-adjacent propulsion are so comparatively small that the math simply does not work. You cannot optimize your way out of this. You cannot upgrade the engine on a Voyager-type probe and get the travel time down from 70,000 years to something a civilization can plan around. The gap between where we are and where we need to be is not an engineering gap. It is a conceptual gap. It requires a completely different way of thinking about how to move through space. And this is exactly why, when Breakthrough Starshot was announced in 2016, it caught the attention of serious physicists rather than being dismissed as another Starship fantasy. Because what it proposed was not a bigger rocket. It was not a faster version of what we already have. It was a genuinely different approach, one that sidesteps the fundamental limitations of conventional propulsion entirely, by using something that does not need fuel, does not need an engine in any traditional sense, and is already moving at the only speed that makes interstellar travel conceivable within a human lifetime. It proposed using light itself, and to understand why that is revolutionary and why it might actually work, we first need to understand something that feels almost paradoxical. The idea that light, the most intangible thing in the universe, can push a physical object. But before we get there, I want to sit for one more moment with the probes, because there is something worth honouring in them. Voyager 1 and Voyager 2 were built by human hands, programmed by human minds, launched on human-made rockets fueled by human ingenuity and decades of accumulated scientific knowledge. They have travelled farther than any object our species has ever created. They are out there right now, in the dark between the stars, still sending their faint signals home across billions of miles, still faithfully reporting what they find. They are one of the most remarkable things our civilization has ever done, and they will never reach another star, not because they failed, but because the universe is so much larger than we were ready for when we built them. What we need now is something entirely new, and remarkably we may already know what it is. The year was 2016. It was April 12th to be precise, and the location was the One World Observatory in New York City, a building that sits at the top of the tallest skyscraper in the Western Hemisphere, with views that stretch for miles in every direction. It was a fitting venue for what was about to be announced. Because on that morning, a small group of people stood at a podium and said something that most of the scientific world had quietly assumed would never be said in a serious context, by serious people, backed by serious money. They said that within a generation we might be able to send a spacecraft to another star, and they were not speaking metaphorically. They had a plan, they had funding, and one of the people standing at that podium was Stephen Hawking. The man who organised and funded the announcement was Yuri Milner, a Russian-born billionaire who had made his fortune in technology investment and had, over the preceding years, quietly become one of the most significant private funders of scientific research on the planet. Milner had already launched a series of initiatives under the name Breakthrough Initiatives, which included a $100 million program called Breakthrough Listen, the most comprehensive scientific search for signs of extraterrestrial intelligence ever conducted. He was not a person who made announcements for publicity. He was a person who identified problems he considered important and applied serious resources to them. And in April of 2016, the problem he chose to address was this: how do we actually get to another star? The project he announced was called Breakthrough Starshot. The initial funding committed was $100 million, and the core proposal, stripped to its essential elements, was this. Rather than building a large, heavy spacecraft powered by conventional rockets or even nuclear engines, Breakthrough Starshot proposed building something almost unimaginably small. A spacecraft roughly the size and weight of a postage stamp, carrying miniaturized cameras, sensors and communication equipment, all packed into a gram-scale chip. This tiny craft, called a Starchip, would be attached to a sail made of material thinner than the thinnest thing you have ever touched. And that sail would be pushed, not by any engine on board, not by any fuel the craft carried, but by an enormous array of lasers on the ground, firing a focused beam of light at the sail and accelerating it to speeds no conventional spacecraft could ever achieve. The target speed was 20% of the speed of light. The target destination was Alpha Centauri. The projected travel time was approximately 20 years, 20 years. I want you to feel the difference between that number and the numbers we discussed in the previous chapter. Voyager 1, our most distant probe, moving at 38,000 miles per hour would need 73,000 years. The Parker Solar Probe, the fastest object we have ever built, would need roughly 6,900 years. Breakthrough Starshot was proposing to do it in 20 years. That is not an incremental improvement. That is not a 10% upgrade on existing technology. It is a reduction in travel time by a factor of more than 3,000. It represents a categorical leap, the kind that happens only a handful of times in the history of human technology. The kind that separates the world before from the world after. The reaction from the scientific community was careful and layered and deeply interesting. There was no outright dismissal, which itself was significant. The physicists who examined the proposal agreed on one fundamental thing. The underlying physics was sound. Light does exert pressure on physical objects. Laser sails are not science fiction. They are a real concept that has been studied seriously in academic literature for decades, with small-scale experiments already demonstrating the basic principle. The proposal was not asking physics to do something impossible. It was asking engineering to do something extraordinarily difficult, and those are very different problems. Impossible means no. Extraordinarily difficult means not yet, but possibly. Hawking's involvement mattered in ways that went beyond his famous name. He'd spent his career thinking about the large-scale structure of the universe, about black holes, about the nature of time, about what physics permits and what it forbids. When he stood at that podium and expressed genuine enthusiasm for Breakthrough Starshot, it sent a signal to the scientific community that this was not a vanity project or a billionaire's daydream. It was a serious scientific proposal worthy of serious attention. Hawking had said publicly, in the years before his death, that he believed humanity needed to become a multi-planetary species to survive in the long run. Breakthrough Starshot represented something even more radical than that. It represented the first credible step toward becoming not just a multi-planetary species, but an interstellar one. What made the announcement feel different from the long history of Starship proposals that had come before? It was precisely that combination. The funding was real, the physics was sound, the team was serious, and the timeline was human scale. Starship concepts had existed for decades. Project Orion in the 1950s and 60s proposed using nuclear explosions to propel a massive spacecraft. Project Daedalus in the 1970s was a British Interplanetary Society study of a fusion-powered probe. Project Icarus in the 2000s revisited and updated those concepts. These were serious engineering studies, and they produced genuine insights. But they also shared a common feature. They required technology that did not yet exist, in some cases technology that was far more speculative than the laser sail approach, and they carried price tags and timescales that placed them firmly in the category of things that might happen someday, in a future too remote to plan toward. Breakthrough Starshot was different because it anchored itself, as much as possible, to technology that either already exists or sits just beyond the current frontier. Miniaturized electronics already approach the scale required for a starship. Lasers of extraordinary power already exist in research settings. Light sails have been tested in space. The gaps are real and substantial, but they are gaps in engineering, not gaps in fundamental physics. And that distinction matters enormously, because engineering problems have a way of getting solved when enough smart people with enough resources focus on them for long enough. We have watched it happen with solar panels, with computing, with gene sequencing, with rocket reusability. The history of technology is a history of engineering problems that once seemed insurmountable quietly becoming routine. Breakthrough Starshot is betting that interstellar propulsion can follow the same arc, and increasingly the people who understand the details best are cautiously beginning to agree. Here is something that sounds like it cannot possibly be true. Light has no mass. You cannot hold it in your hand. You cannot weigh it on a scale. It passes through glass, bounces off mirrors, and travels across the universe without any of the properties we normally associate with physical things. And yet, light pushes. When a beam of light strikes a surface, it exerts a force on that surface. A tiny force, almost undetectable under normal circumstances, but a real force, measurable in laboratories, predicted by the equations of physics, and observed consistently in experiments going back more than a century. Light carries momentum, and momentum, when transferred from one object to another, produces motion. This is not speculation. This is not a theoretical possibility awaiting confirmation. It is a measured, documented, repeatable physical fact, and it is the foundation upon which the entire concept of a laser sail rests. The phenomenon is called radiation pressure. It arises from the quantum nature of light. Light is made up of particles called photons, and while photons have no mass, they do carry energy. And energy is equivalent to momentum in ways that Einstein's equations make precise and unavoidable. When a photon strikes a surface and is absorbed, it transfers its momentum to that surface. When a photon strikes a reflective surface and bounces back, it transfers twice as much momentum, because the reversal of direction doubles the impulse. This is why a perfectly reflective sail is more efficient than an absorbing one. Every photon that bounces off the sail pushes the sail a little harder than a photon that is simply absorbed. The physics is elegant and it is exact, and it has been known in principle since James Clerk Maxwell developed his theory of electromagnetism in the 1860s. But if light exerts pressure, why don't we feel it? Why doesn't sunlight push us around as we walk outside on a bright afternoon? The answer is that the force involved is extraordinarily small under normal circumstances. The radiation pressure from direct sunlight on a surface of 1 square meter is roughly 9 micronewtons. To put that in terms you can feel, it is approximately the weight of a single grain of sand resting on your fingernail. For any object with meaningful mass, that force is completely overwhelmed by gravity, air resistance, and every other physical force in the environment. It is there, but it is invisible against the noise of the everyday world. The trick, then, is not to make the force larger. The trick is to make the object being pushed almost impossibly light, and to use an extremely powerful, focused beam of light rather than diffuse sunlight. That is precisely what Breakthrough Starshot proposes to do. Now, the idea of using light to push a spacecraft is not new. It has a history that stretches back decades in both science and science fiction. The concept of a solar sail, a large reflective sheet that catches the gentle push of sunlight the way a nautical sail catches wind, has been seriously studied since at least the 1920s, when the Russian scientist Konstantin Tsiolkovsky and others began exploring the mathematics of space propulsion. Solar sails have actually been built and launched. Japan's Ikaros mission in 2010 was the first spacecraft to successfully demonstrate solar sailing in deep space, using a 14-meter square sail to gain measurable thrust from sunlight alone. NASA's NanoSail D and the Planetary Society's LightSail missions have further demonstrated the technology. Solar sailing works. It is real. The problem is that sunlight is diffuse and weak, and the further you travel from the sun, the weaker it becomes. A solar sail would accelerate a spacecraft, but only to speeds that remain far too slow for interstellar travel. This is where the laser changes everything. Instead of relying on the gentle, unfocused radiation of the sun, Breakthrough Starshot proposes using an enormous array of ground-based lasers, all focused into a single coherent beam of extraordinary power aimed at the sail of the departing spacecraft. The numbers involved are staggering. The proposed laser array would need to deliver somewhere in the range of 100 gigawatts of power into the sail during the acceleration phase. 100 gigawatts. For comparison, the total electricity generating capacity of the United Kingdom is roughly 80 gigawatts. The entire power output of a large nation, focused into a beam of light, aimed at a sail the size of a few square meters for a period of perhaps 10 minutes. During those 10 minutes, the Starship and its sail would accelerate from a standing start to 20% of the speed of light. It would be the most violent acceleration ever applied to a human-made object, and the most powerful use of directed energy in the history of our civilization. 20% of the speed of light. Let me give you a sense of what that means in practical terms. The speed of light is approximately 186,000 miles per second. 20% of that is about 37,200 miles per second. In 1 second, the Starship would travel a distance roughly equivalent to going around the entire Earth 1.5 times. In 1 minute, it would cover more than 2 million miles. The Moon is about 239,000 miles away. At 20% of light speed, the Starship would pass the Moon's orbital distance in less than 7 seconds. It would pass Mars's closest approach distance in a matter of minutes. It would cross the entire span of our solar system in a matter of days, and it would reach Alpha Centauri in approximately 20 years. That is what laser propulsion at 20% of light speed actually means, translated into the geography of our cosmic neighborhood. There is something almost philosophically beautiful about this approach, and I want to name it before we move on, because I think it deserves a moment of quiet appreciation. Every other form of spacecraft propulsion we have ever used involves carrying the energy source with you. Chemical rockets carry fuel and oxidizer. Nuclear propulsion carries fissile material. Ion drives carry propellant. All of them are limited by what they can carry, which is limited by mass, which creates a fundamental ceiling on how fast they can go. The laser sail breaks that ceiling completely. The energy source stays on the ground. It is never on the spacecraft. The spacecraft carries nothing except its instruments and its sail. It is, in a profound sense, the lightest possible interstellar vehicle, a postage stamp-sized chip of electronics riding a beam of light across the void. The universe permits this. The physics allows it. And that permission, that allowance, is perhaps the most extraordinary gift the laws of nature have quietly left waiting for us to discover. Pick up a postage stamp, hold it between your fingers and look at it. Feel how light it is, how thin, how almost absurdly small relative to the distances it travels through the postal system. Now imagine that object is a spacecraft. Not a model of a spacecraft, not a component of a spacecraft, but the entire spacecraft itself, containing everything it needs to cross 4.24 light-years of interstellar space, photograph another star system, and transmit that data back to Earth across a gulf so vast that the signal takes 4 years to arrive. That is what the Starship is. That is what Breakthrough Starshot is asking engineers and physicists and materials scientists to build. And the most astonishing thing about it is not that the challenge is impossible. The most astonishing thing is how close we already are. The concept of the Starship emerges directly from one of the most remarkable technological trends of the past half-century. Since the invention of the integrated circuit in the late 1950s, the components of computing have been shrinking at a pace that still seems almost miraculous when you trace it across time. The first electronic computers filled entire rooms. The computers that guided the Apollo missions to the moon fit in a box the size of a large suitcase and were less powerful than a modern pocket calculator. The smartphone in your pocket today contains more computing power than all of NASA's combined computational resources at the time of the moon landings. This process of miniaturization has not stopped. It has continued, and in some areas it has accelerated, driven by advances in nanotechnology, photonics, and materials science that are producing electronic components of almost unbelievable smallness and efficiency. The Starship needs to carry several distinct systems, all packed into a total mass of roughly 1 gram. 1 gram is about the weight of a paperclip. Within that gram, the design calls for cameras capable of capturing images of an alien star system in multiple wavelengths of light, including visible light and potentially infrared. It needs navigation sensors that can determine the chip's orientation and position in space without any external reference points. It needs communication equipment capable of transmitting data across 4.24 light-years back to Earth, using a laser of its own. It needs a power source sufficient to run all of these systems during the 20-year journey and during the brief, critical minutes of the flyby. And it needs a computer to coordinate everything, make autonomous decisions without any possibility of real-time instruction from Earth, and execute the mission with essentially no margin for error. All of that in 1 gram. Here is the thing most people don't realize about this list of requirements. Every single item on it either already exists in prototype form, or is a near-term extrapolation of technology currently under active development. The cameras are perhaps the most straightforward element. Modern smartphone cameras pack extraordinary imaging capability into chips that weigh a fraction of a gram. Scientific-grade image sensors have been miniaturized to scales that would have seemed fantastical 20 years ago. The navigation systems are trickier because space presents unique challenges that terrestrial sensors are not designed for, but the fundamental components, accelerometers, gyroscopes, star trackers in miniaturized form, are all within reach of current or near-future engineering. The power source is one of the more interesting challenges. Solar panels become less useful as the craft moves farther from the sun, and the chip needs to operate for decades. The proposed solution involves ultra-thin photovoltaic cells that harvest what little sunlight is available in the outer solar system, combined with extremely low-power electronics that can run on minimal energy for years at a time. The communication system deserves special attention because it is one of the most technically demanding elements of the entire mission. The Starship needs to send a laser signal back to Earth from 4.24 light-years away. The signal will be vanishingly faint by the time it arrives, diluted across the vast distance it has travelled. Detecting it will require large Earth-based telescopes working in coordination, filtering noise and isolating the specific wavelength of the Starship's laser from the background radiation of the cosmos. But this is not a new problem. Radio astronomers have been doing something similar for decades with signals from distant spacecraft, and the techniques for detecting extremely faint signals against noisy backgrounds are well developed. The difference in scale is significant, but the principle is understood, and there is genuine confidence in the research community that the communication challenge is solvable. The sail is technically a separate component from the Starship itself, but together they form the complete spacecraft, and the sail's properties are as demanding as anything else in the design. The sail needs to be large enough to catch sufficient laser energy to accelerate the gram-scale chip to 20% of light speed. Current designs call for a sail of roughly 4 meters by 4 meters, an area of 16 square meters, but it needs to be extraordinarily thin and extraordinarily light, because any additional mass requires more laser energy to accelerate, which requires a more powerful laser array, which increases cost and complexity in ways that compound rapidly. The target thickness is just a few hundred nanometers, thinner than the thinnest soap bubble you've ever seen. Materials that approach these specifications already exist in research settings. Graphene, the single-atom thick sheet of carbon atoms whose discovery won the Nobel Prize in Physics in 2010, is one candidate. Engineered metamaterials with carefully designed optical properties are another. The field is active and advancing. There is something I find quietly extraordinary about the contrast at the heart of the Starship concept. On one hand, the mission it is being asked to perform is the most ambitious thing our civilization has ever attempted. Travel to another star, photograph an alien world, send back the first images of a planetary system beyond our own. On the other hand, the vehicle that will perform this mission weighs the same as a paperclip, and could fit in the palm of your hand. There is a poetry in that contrast that I think matters. We tend to imagine grand journeys requiring grand vehicles. We picture massive rockets, enormous fuel tanks, sprawling spacecraft with rotating sections and vast solar arrays. The Starship inverts that intuition entirely. It says that the key to crossing interstellar space is not to build something bigger, it is to build something smaller than we ever thought a spacecraft could be, and to push it with something that costs nothing to carry, because it never boards the craft at all. The energy stays on the ground. The spacecraft goes to the stars. And between those two facts lies one of the most elegant ideas in the history of human engineering. Imagine standing in a desert at night. The air is perfectly dry, the sky is perfectly clear, and there is no light pollution for hundreds of miles in any direction. The stars above you are sharp and dense, a river of light across the darkness. Now imagine that somewhere beneath your feet, buried in the rock and sand of this remote place, is the most powerful directed energy system ever constructed by human hands. A machine that, when activated, focuses the combined output of thousands of individual laser units into a single coherent beam of light so powerful that it could accelerate a gram-scale spacecraft to 20% of the speed of light in approximately 10 minutes. A machine that draws more electricity than some small nations consume in a year, fires it upward through the atmosphere in a pulse of focused coherence, and sends a postage stamp-sized probe on a journey to another star. This machine does not yet exist, but the physics that would govern it is fully understood, and the engineering path to building it, while extraordinarily difficult, is increasingly visible to the people who study it most closely. The laser array proposed for Breakthrough Starshot is not a single laser. That distinction matters enormously, because a single laser of the required power, somewhere in the range of 100 gigawatts, would be essentially impossible to build with foreseeable technology. The heat alone would destroy any known material. The optics required to focus such a beam would be beyond anything currently manufacturable. Instead, the proposed architecture involves an array of perhaps millions of individual laser units, each one modest in its own right, all firing simultaneously and all phase-locked together so that their beams combine coherently into a single focused point of light at the target. This technique, called phased array laser combining, is the central enabling technology of the entire Breakthrough Starshot concept, and it is a technique that already exists in smaller forms in military and research settings around the world. Phased arrays work by coordinating the timing of multiple emitters so precisely that their waves align and reinforce each other rather than cancelling each other out. You can think of it like a choir. A single human voice singing a note produces a certain volume of sound. 1,000 voices singing exactly the same note at exactly the same pitch and exactly the same time produces something dramatically more powerful than any individual voice. The key word is exactly. If even a small number of voices are slightly out of sync, the coherence breaks down and the combined effect is diminished. The same principle applies to lasers. Each individual unit in the array must be synchronized to the others with a precision measured in fractions of a wavelength of light. A tolerance so tight it requires active feedback systems, monitoring and adjusting the phase of every emitter in real time, thousands of times per second. It is one of the hardest engineering problems in the entire project. It is also one of the problems that researchers are already making measurable progress on. The physical scale of the array is another challenge that stops you in your tracks when you first encounter the numbers. To deliver 100 gigawatts of laser power through Earth's atmosphere and focus it on a sail 4 meters across that is already accelerating rapidly away from the planet, the array would need to span roughly 1 kilometer in diameter. 1 kilometer of laser emitters, phase-locked together, tracking a moving target through the atmosphere with extraordinary precision, for a firing duration of perhaps 10 minutes. The site would need to be at high altitude to minimize atmospheric distortion, in a location with exceptional seeing conditions and minimal cloud cover. High desert plateaus, similar to the sites where the world's most powerful optical telescopes are built, in places like the Atacama Desert in Chile or the high plateaus of Tibet, have been discussed as potential candidates. The array would be, without question, the largest and most powerful directed energy installation ever built by our civilization. The atmosphere itself presents a significant complication that deserves its own moment of attention. Light passing through air is not perfectly clean. It gets scattered, absorbed, and distorted by turbulence, humidity, and the density gradients that make stars twinkle when you look at them from the ground. Professional observatories deal with this using a technique called adaptive optics, in which a deformable mirror adjusts its shape hundreds of times per second to compensate for atmospheric distortion in real time. The laser array for Breakthrough Starshot would need something analogous but far more powerful and precise. The beam must not only be kept coherent as it exits the array, but it must remain focused on the sail as the sail accelerates away at a rate that changes from moment to moment. Tracking a sail moving at increasing fractions of the speed of light, while simultaneously compensating for atmospheric turbulence, while maintaining phase coherence across a kilometre-wide array, is an engineering challenge of a complexity that has few precedents in human history. And then there is the question of what the beam does to anything that gets in its way. 100 gigawatts of focused laser energy is not a gentle thing. It is, in the most literal sense, a weapon of extraordinary power. This has not escaped the notice of physicists, engineers, or governments. The geopolitical dimensions of building a ground-based laser installation of this magnitude are substantial and complicated. A system capable of accelerating a gram-scale sail to relativistic speeds is, by definition, a system capable of delivering enormous energy to a point target at very long range. The dual-use nature of the technology is one of the reasons why international coordination will be essential, and why some researchers believe the array should be built and operated under the auspices of an international scientific body rather than any single nation. The political challenges of that kind of coordination are real, and they are not trivial, but they are human problems, not physics problems, and human problems historically have a better track record of eventually getting solved. What I find most striking about the laser array, when I sit with the full picture of what it would involve, is the way it reframes our intuition about where the hard part of interstellar travel actually is. We tend to imagine the challenge of reaching another star as something the spacecraft must overcome. The journey, the distance, the emptiness. But Breakthrough Starshot relocates the hard part entirely. The spacecraft, the Starship, is the easy part. It is a gram of electronics and a thin sail. The hard part stays on the ground. The hard part is the machine that launches it. The kilometre-wide array of phase-locked lasers drawing more power than a nation, firing a beam of coherent light through the atmosphere, and pushing a postage stamp-sized chip to 20% of light speed in the time it takes to brew a cup of coffee. The stars have not moved, the distance has not shrunk, but the place where human ingenuity must do its hardest work has shifted from the void between the stars to the surface of our own planet. And somehow, that makes the whole thing feel both more possible and more extraordinary than ever. Once the laser array falls silent and the Starship is on its way, something shifts in the nature of this mission that deserves to be named honestly. The probe is alone. Completely, irrevocably, and permanently alone. It is moving at 20% of the speed of light through a region of space where no human instrument has ever operated at these velocities, where the environment is governed by physical forces that our probes near Earth never have to contend with in any serious way. There is no possibility of repair. There is no possibility of real-time course correction from Earth. There is no retrieval mission if something goes wrong. Whatever the craft encounters in the dark between the stars, it must face entirely on its own, with every contingency the engineers could imagine already woven into its design before the laser fired. The mission is, in the most literal sense, a one-way throw across the void. And the void, as it turns out, is not as empty as it looks. The single, most immediate and terrifying physical threat to the Starship during its 20-year crossing is something that sounds almost trivial until you run the numbers. Dust. Interstellar space is not a perfect vacuum. It contains traces of gas and microscopic particles, grains of matter scattered at extraordinarily low densities across the gulf between stars. Under normal circumstances, at the speeds of conventional spacecraft, these particles are essentially irrelevant. A probe moving at 38,000 miles per hour might occasionally collide with a dust grain and suffer no meaningful consequence whatsoever. But the Starship is not moving at 38,000 miles per hour. It is moving at roughly 37,000 miles per second. At that velocity, a single grain of interstellar dust, an object so small it would be invisible to the naked eye, strikes the sail or the chip with the kinetic energy of a small explosive. The impact is not a gentle tap. It is a micro-collision releasing energy, capable of punching through materials, vaporizing surface layers, and potentially destroying delicate electronics in a fraction of a second. The engineers working on Breakthrough Starshot are acutely aware of this problem, and several approaches have been proposed to address it seriously. The first involves specialized shielding on the leading edges of the sail and chip, using materials chosen for their ability to absorb or deflect micro-impacts without catastrophic structural failure. Certain engineered composites and ultra-hard thin-film coatings are under active investigation as candidates. The second approach involves geometry, orienting the craft so that the smallest possible cross-sectional area faces the direction of travel, reducing the probability of a damaging strike during the crossing. The third and perhaps most elegant approach is redundancy at the mission level. Rather than depending on a single Starship surviving the crossing intact, Breakthrough Starshot envisions launching a fleet of them, potentially hundreds or thousands in a single coordinated burst from the laser array. If even a small fraction survive the 20-year gauntlet and reach Alpha Centauri functional, the mission succeeds. The fleet approach transforms what would otherwise be a devastating single point of failure into a manageable statistical probability. Beyond dust, there is radiation. Interstellar space is permeated by cosmic rays, high-energy particles accelerated to near-light speeds by supernova explosions, and other violent astrophysical events distributed throughout the galaxy. These particles pierce conventional spacecraft shielding and damage electronics, with a reliability that has been a persistent engineering headache for every deep space mission ever flown. The Starship, with its gram-scale electronics and almost non-existent shielding mass, is particularly exposed to this threat. Over 20 years of continuous travel through the interstellar radiation environment, cumulative damage to the chip's circuits could degrade or destroy its ability to function by the time it finally reaches Alpha Centauri. Radiation-hardened electronics already exist for space applications, and the extreme miniaturization required for the Starship actually confers certain advantages here, since smaller transistors can in some configurations tolerate higher radiation doses before failing. But designing a chip that survives 2 decades of interstellar cosmic ray bombardment and still executes its mission with precision at journey's end is a material science and engineering challenge, that has no direct precedent in the history of spaceflight. There is also a threat that exists not in deep space, but in the first moments of the mission itself, during the laser firing phase, and it is one of the subtlest and most technically vexing problems in the entire concept. When the beam pushes the sail, it must push it with perfect symmetry. If the beam drifts even fractionally off-center, the uneven pressure will cause the sail to tilt. A tilted sail catches the beam at an angle, which generates a sideways force component, which tilts the sail further, which amplifies the sideways force in a runaway feedback loop that could spin the craft out of control within seconds. The sail must be designed to resist this instability passively, through a geometry and mass distribution that naturally keeps it centered in the beam, the way a shuttlecock naturally rights itself in flight. Researchers have identified sail shapes, including slightly concave designs reminiscent of a shallow bowl, that appear to provide this kind of inherent beam riding stability. The problem is not yet fully solved, however, and it remains one of the areas where the most urgent theoretical and experimental work is currently concentrated. Then there is the long silence. 20 years of flight with no ability to diagnose problems, reroute systems, or apply any fix whatsoever from the ground. The speed of light itself becomes the enemy here. Even if the Starship could transmit a distress signal the moment something started going wrong, that signal would take years to reach Earth, and any response would take years more to travel back. By the time a human engineer on the ground even knew something had failed, the probe would have already lived or died by its own autonomous systems thousands of times over. Every decision the Starship makes during its journey must be made by the chip itself, governed by software and hardware designed to anticipate failure modes that have never been observed in any spacecraft operating at these speeds. The level of autonomous resilience required goes far beyond anything currently deployed in space missions. It is, in effect, asking for a spacecraft that can diagnose and manage its own survival for 2 decades, in conditions no machine has ever endured, without any help from home. What strikes me most about the full inventory of threats facing the Starship is not any single problem in isolation. It is the cumulative portrait they paint of interstellar space as an environment. We tend to think of the void between stars as peaceful, as the dark quiet that cradles the distant lights we call constellations, and in a human experiential sense that is true. But for a gram-scale chip moving at 20% of light speed, that quiet dark is a gauntlet of dust impacts, radiation damage, beam riding instability, and 2 decades of enforced solitude with no backup. The engineers designing the mission know all of this. They are not pretending the threats do not exist. They are building solutions to each one, running simulations, testing materials, developing autonomous software architectures, and refining sail geometries. None of those solutions are finished yet. But the fact that they are being built at all, carefully and seriously, by real scientists with real funding, is itself one of the most remarkable things happening in science right now. The gauntlet is real. The response to it is already underway. In August of 2016, just 4 months after Breakthrough Starshot was announced to the world, astronomers made a discovery that changed the emotional texture of the entire mission in a single afternoon. They found a planet. Not around a distant, unreachable star on the far side of the galaxy. Not around a star that would require centuries of travel, even under the most optimistic projections. They found a planet orbiting Proxima Centauri, our nearest stellar neighbour, the very star that Breakthrough Starshot was already aiming for. The planet was named Proxima Centauri b, or more simply, Proxima b, and the details of what astronomers could determine about it from Earth were enough to make even the most reserved scientists pause and feel, quietly and privately, something that science does not often permit itself to feel: hope. Proxima b was detected using a technique called the radial velocity method, which measures the tiny wobble a planet induces in its host star as it orbits. The planet's gravitational pull tugs the star very slightly toward and then away from Earth with each orbit, and this motion produces a measurable shift in the wavelength of the star's light. By tracking that shift with extraordinary precision over many months of observation, astronomers were able to confirm the existence of a planet with a minimum mass of roughly 1.27 times the mass of Earth. That places it firmly in the category of rocky terrestrial worlds, the category our own planet belongs to, rather than the gas giant category that Jupiter and Saturn represent. It orbits Proxima Centauri once every 11.2 Earth days, which sounds startlingly fast, but the relevant question is not how long the year is. The relevant question is where the planet sits relative to its star's habitable zone. The habitable zone, sometimes called the Goldilocks zone, is the range of orbital distances at which a planet could theoretically maintain liquid water on its surface given the right atmospheric conditions. Not too hot, not too cold. For our Sun, that zone sits at roughly the distance where Earth orbits, about 93 million miles from the star. For Proxima Centauri, a red dwarf star far cooler and dimmer than our Sun, the habitable zone sits much closer in, because the star radiates far less energy. And Proxima b, despite its 11-day orbit that would place it scorchingly close to a star like our Sun, sits almost precisely in the centre of Proxima Centauri's habitable zone. The temperatures on its surface, depending on its atmosphere, could potentially allow liquid water to exist. And where liquid water can exist, the possibility of life cannot be casually dismissed. But here is where the picture becomes more complicated and more interesting than a simple announcement of a potentially habitable world would suggest. Proxima Centauri is not a gentle star. It is a red dwarf, and red dwarfs have a well-documented tendency toward violent magnetic activity. They produce stellar flares, sudden releases of enormous amounts of energy from the star's surface, with a frequency and intensity that vastly exceeds what our own Sun produces. Proxima Centauri flares regularly and sometimes dramatically. In 2019, astronomers observed a flare from Proxima Centauri that was roughly 100 times brighter than any flare ever recorded from our Sun. A flare of that intensity, striking a planet orbiting as closely as Proxima b does, could in principle strip away atmospheric gases, bombard the surface with ultraviolet and X-ray radiation, at levels lethal to life as we know it, and do so repeatedly over billions of years of the planet's history. Whether Proxima b has retained an atmosphere despite this bombardment is genuinely unknown. It depends on factors we cannot yet measure from Earth, including the strength of the planet's magnetic field, the original composition and density of its atmosphere, and the precise history of the star's flaring activity over geological timescales. Some researchers argue that the planet's atmosphere would have been stripped long ago, leaving a bare, irradiated rock with no possibility of habitability. Others point out that certain atmospheric compositions are more resistant to stellar stripping than others, that geological processes can replenish atmospheric gases over time, and that life, if it ever arose on Proxima b, might have had billions of years to adapt to conditions very different from those we consider normal. The honest scientific answer is that we do not know. We genuinely, at this moment in history, do not know whether Proxima b is a living world, a dead rock, or something in between that we have no category for yet. And this uncertainty, this profound and magnificent uncertainty, is precisely what makes it a destination worth crossing 25 trillion miles to visit. Because a starship arriving at Proxima b would not be reading papers, or running simulations or making inferences from wobbles in starlight measured across light years. It would be there. It would be in the same system as this world, close enough to image its surface, to measure the composition of any atmosphere that exists, to detect the signature of liquid water, to search for the specific chemical patterns that on Earth are produced by biological processes. The instruments required to do these things at flyby speeds and gram-scale masses are extraordinarily challenging to miniaturize and operate. But they are not, in principle, beyond what physics and engineering allow. What the starship might return from those minutes of close approach is a set of data that would rewrite every major question human civilization has ever asked about its place in the universe. I want you to sit with that for a moment in the particular quiet of tonight. There is a world orbiting the star closest to our own. We have known about it for less than a decade. We do not know if it has an atmosphere. We do not know if it has water. We do not know, with any certainty whatsoever, whether anything has ever lived or is living there right now, at this very moment, as you listen to these words in the dark. Something on that world, if anything is there, has been under that cool red sun for billions of years, without any knowledge that 4.24 light-years away, on a pale blue dot orbiting a different star, creatures made of carbon and water have been looking up at the night sky and wondering. And now those creatures are building a machine to come and look. The first visitor from Earth to another star system may arrive at Proxima b within the lifetime of people alive today. What it finds there or does not find will be one of the most consequential moments in the history of our species, And that is not hyperbole. That is simply the weight of what is actually at stake. There is a particular kind of human patience that I find almost unbearably moving when I think about it clearly. It is the patience of waiting for something you know is coming, something you calculated and planned and built and launched, but that will not arrive in your lifetime, or perhaps in the lifetime of anyone you will ever meet. It is the patience of planting a tree whose shade you will never sit under, of writing a letter to a reader not yet born, of building a cathedral that will take 200 years to complete and laying the first stone anyway, because the cathedral matters more than your presence at its completion. That is the emotional texture of Breakthrough Starshot when you follow it all the way to its end. And the end, when you examine it closely, contains one of the most quietly heartbreaking constraints in the entire mission. After 20 years of travel across 25 trillion miles of interstellar void, the Starship will have approximately 1 hour in the vicinity of the Alpha Centauri system, perhaps less, and then it will be gone. This is the flyby problem, and it arises directly from the same physics that makes the mission possible in the first place. The Starship reaches Alpha Centauri travelling at 20% of the speed of light. That speed is what makes the 20-year transit time achievable, but that speed is also what makes stopping, or even slowing down meaningfully, essentially impossible within the mass and energy budget of the mission. To decelerate from 20% of light speed to orbital velocity around a distant star, you would need to carry an enormous amount of propellant, or install some kind of braking system, neither of which is compatible with a gram-scale spacecraft riding a beam of light. The physics that enables the journey also ensures that the journey cannot end with a graceful arrival, an orbit insertion, a gentle descent into a new star system. It ends with a blur, a brief blazing passage through the Alpha Centauri system, at a speed that makes everything we consider fast seem motionless by comparison. Let me make this concrete, because the numbers are important to feel rather than just understand intellectually. At 20% of the speed of light, the Starship is covering roughly 37,000 miles every second. The distance between Earth and the Moon is about 239,000 miles. The Starship crosses that distance in approximately 6.5 seconds. The diameter of the entire inner solar system, from the Sun out to roughly the orbit of Mars, is perhaps 300 million miles across. The Starship covers that distance in about 2 hours and 15 minutes. The Alpha Centauri system, from its outermost regions down to close approach with Proxima Centauri, spans a region perhaps comparable in scale to our own solar system. The Starship's window to do meaningful science, to image Proxima b, to measure atmospheric signatures, to capture the data that will justify the entire mission, may last no more than a few hours, and the closest, highest resolution portion of that window may last minutes. In cosmic terms, it is a single held breath. Now add another layer to this. Even after the flyby is complete, and the Starship has gathered whatever data it could capture in those frantic minutes of close approach, the data does not arrive on Earth immediately. The signal the chip transmits, travelling at the speed of light, takes 4.24 years to cross the distance back to us. The probe arrives at Alpha Centauri roughly 20 years after launch. The data from the flyby begins arriving on Earth roughly 24 years after launch. The people who receive that signal, who sit at radio telescopes or optical receivers and watch the first images of another star system resolve out of the noise, will be people who in most cases were not yet adults when the mission launched. The graduate students working on the receiving infrastructure today will be in their 40s and 50s. The project directors who announced Breakthrough Starshot in 2016 are likely to be gone. The data arrives as a kind of message from a past that the future has been waiting for, across both space and time simultaneously. There is a dimension to this that goes beyond engineering, and I want to name it because I think it matters to how we understand what this mission actually is. Every space mission we have ever flown has been, in some sense, within the span of a human career. The scientist who designed Voyager in the 1960s and 70s was still alive to see it cross the heliopause in 2012. The engineers who built the Mars rovers have watched them drive across the Martian surface in real time, celebrating each milestone with people who shared the original dream. Even the longest duration missions have remained within the compass of a single working lifetime. Breakthrough Starshot breaks that pattern completely and permanently. It inaugurates a new category of human endeavour, the multi-generational scientific mission, a project that is begun by one generation, executed by the universe across 2 decades of empty space, and received by a generation that has only ever known the mission as history and aspiration, never as active work in progress. The flyby constraint also forces a kind of ruthless prioritization in the mission's scientific design that I find clarifying in an unexpected way. When you have minutes rather than months, you cannot afford ambiguity about what you're looking for. The instruments must be optimized in advance for the most critical questions, and those questions must be chosen carefully because you will not have a second pass. Is there an atmosphere on Proxima b? What is its composition? Is there liquid water visible on the surface? Are there chemical signatures that on Earth are associated with biological activity? These are not the only questions worth asking about this world, but they are the questions worth asking first, in the few frantic minutes of closest approach, with instruments the size of a thumbnail, across a distance that light takes 4 years to cross. The constraints of the mission concentrate its purpose in a way that makes it, paradoxically, more focused and more meaningful than a mission with unlimited time might be. And through all of this, there runs something I cannot quite categorize as either sadness or beauty, but which feels like both at once. The engineers who will solve the hardest remaining problems in Breakthrough Starshot may never know if their solutions worked. The people who build the laser array may be elderly or dead by the time it fires. The generation that launches the fleet of starships will spend the rest of their lives knowing that somewhere out there, moving through the dark at unimaginable speed, is something they made, aimed at a destination they will never see confirmed. And then, 24 years after the launch, on a morning that none of the founders may live to see, somewhere on Earth a receiver will pick up a faint signal, a whisper of laser light from 4.24 light-years away. And in that signal, if all has gone well, will be the first images ever taken of another star system from within that system itself. 1 second of science, 24 years in the making, the most patient photograph in human history. Breakthrough Starshot is not the only road that has been proposed toward the stars. It is important to say that clearly, because the history of interstellar propulsion concepts is richer and stranger and more deeply human than most people realize. Long before Yuri Milner stood at a podium in New York and announced laser sails and gram-scale probes, other scientists and engineers had looked at the same impossible distance and proposed their own answers. Some of those answers were enormous, some were nuclear, some were biological in the most profound sense, involving not machines at all but human beings, living and dying across generations in the dark between stars. Each of these concepts tells us something different about how our civilization has understood the problem of interstellar travel, and each of them illuminates, by contrast, exactly what makes Breakthrough Starshot so unusual and so potentially significant. The oldest serious interstellar propulsion concept with genuine scientific credentials is also one of the most audacious ever conceived. It was called Project Orion, and it was developed in the late 1950s and early 1960s by a group of physicists at General Atomics that included some of the most brilliant scientific minds of the 20th century, among them Freeman Dyson, one of the great theoretical physicists of the post-war era. The concept behind Project Orion was breathtakingly direct. You build a massive spacecraft with a thick steel plate at its rear, called a pusher plate. You drop nuclear bombs out of the back of the ship one after another, and let the explosions push against the plate, accelerating the spacecraft. Each detonation provides an enormous impulse. A sequence of hundreds or thousands of detonations could, in principle, accelerate a ship of thousands of tons to a few % of the speed of light. Dyson calculated that an Orion-type vessel could reach Alpha Centauri in approximately 130 years. The physics was sound. The engineering was feasible with technology that existed in 1960. The project was cancelled not because it could not work, but because the Partial Nuclear Test Ban Treaty of 1963 made it illegal to detonate nuclear weapons in space. Project Daedalus came next, in the 1970s, developed by the British Interplanetary Society as a rigorous engineering study of what an unmanned interstellar probe might actually look like. Daedalus replaced nuclear fission with nuclear fusion, specifically the fusion of helium-3 and deuterium in a pulsed ignition system, not entirely unlike the Orion concept, but cleaner, more efficient, and theoretically more controllable. The proposed spacecraft was enormous, roughly 2 times the size of a Saturn V rocket by mass, and would require 50,000 metric tons of helium-3 as fuel, an isotope so rare on Earth that the study proposed mining it from the atmosphere of Jupiter. Daedalus was designed to reach Barnard's star, about 6 light-years away, in approximately 50 years. It would arrive as a flyby, not an orbiter, and would deploy probes into the target system during its brief passage. The study was never intended to produce a buildable spacecraft on any near-term timeline. It was intended to establish that interstellar travel was a serious engineering problem, rather than a fantasy, and in that aim it succeeded completely. Project Icarus, launched in 2009 as a successor to Daedalus, updated and refined the fusion propulsion concept with 4 decades of additional scientific knowledge. The Icarus study team grappled with the same fundamental challenge that has always confronted fusion propulsion proposals. We do not yet have controlled fusion power. Not on Earth, not in space, not anywhere. The promise of fusion energy has been approximately 30 years away for the past 70 years, a fact that scientists acknowledge with a mixture of rueful humour and genuine frustration. Fusion propulsion for interstellar travel requires not just that we achieve controlled fusion, but that we achieve it at efficiencies and power densities far beyond anything currently demonstrated in any laboratory on the planet. It is not physics fiction. The reactions work, but the engineering required to harness them at the scales demanded by interstellar propulsion remains firmly in the category of things that are theoretically possible, but practically very far away. Antimatter propulsion occupies a fascinating and somewhat extreme position in the landscape of interstellar concepts. Antimatter is the most energy-dense fuel imaginable by the laws of physics as we currently understand them. When a particle of matter meets its antimatter counterpart, both are converted entirely into energy, with 100% efficiency, releasing far more energy per unit mass than any chemical or nuclear reaction. An antimatter rocket, if you could build one, would be the most powerful propulsion system physics permits. It could theoretically accelerate a spacecraft to a significant fraction of the speed of light. The problem is not the concept. The problem is the antimatter itself. Producing antimatter requires enormous amounts of energy, particle accelerators, and extraordinarily complex containment systems. As of today, the total amount of antimatter ever produced by all the particle accelerators in the history of human civilization would not be enough to boil a cup of water. Scaling antimatter production to the quantities needed for interstellar propulsion is so far beyond current capability that it functions, for practical purposes, less as an engineering challenge and more as a long-term civilizational aspiration. Generation ships represent perhaps the most philosophically provocative alternative of all, because they sidestep the speed problem entirely by accepting it. Rather than accelerating a probe or a crewed ship to a fraction of light speed, a generation ship travels at speeds achievable with plausible near-future propulsion, perhaps 1% of light speed or less, and simply accepts that the journey will take hundreds or thousands of years. The crew who departs will never arrive. Their children will not arrive. Their grandchildren's grandchildren born in the ship knowing no other world will be the ones who see Alpha Centauri grow from a bright star to a sun. The concept raises profound ethical questions about the consent of the generations born into a journey they did not choose, about the social structures required to maintain a civilization in a closed environment for centuries, and about what kind of people arrive at the destination after 1,000 years of selection pressure in an artificial world. Generation ships have been a rich subject for science fiction, because the human dimensions of the concept are vast and complicated in ways that no engineering study can fully address. When you lay all of these roads out alongside Breakthrough Starshot, something becomes clear that might not be obvious at first glance. Every alternative, nuclear pulse, fusion drive, antimatter rocket, generation ship, either requires technology that does not yet exist by a very large margin, or requires timescales of travel so long that the mission becomes a civilizational project rather than a scientific one. Breakthrough Starshot, by contrast, is built on physics that already works and technology that either exists or sits just beyond the current engineering frontier. It does not require controlled fusion. It does not require antimatter. It does not require anyone to live and die in a ship crossing the void. It requires lasers, miniaturized electronics, and an extraordinarily thin sail. The engineering gaps are real and significant, but they are gaps you can point to on a roadmap, assign research teams to, and make measurable progress on year by year. That combination of grounded physics, existing technology, and a clear engineering path is rarer in the history of interstellar proposals than it might appear. And it is precisely what makes Breakthrough Starshot the most credible first step toward the stars that our civilization has yet conceived. There is a particular kind of signal that cuts through noise more reliably than almost any other in the modern world. It is not a press conference. It is not a scientific paper, however rigorous. It is not an announcement, however bold. It is money. Not promised money, not conceptual funding, not the kind of investment that exists on a slide in a presentation, but actual committed capital flowing toward actual research teams doing actual work on actual problems. Money has a way of separating serious intent from wishful thinking that words alone cannot achieve. And when you look at what has been happening in the world of interstellar propulsion research since the Breakthrough Starshot announcement in 2016, the money tells a story that is far more advanced and far more encouraging than most people outside the field are aware of. The initial $100 million committed by Yuri Milner to Breakthrough Initiatives was not spent on a single grand engineering project. It was deployed strategically in the way that serious research funding works when the goal is to make progress on multiple fronts simultaneously. Grants went to university research groups working on laser physics, on sail materials, on miniaturized electronics, on phased array technology, on atmospheric compensation systems. Research contracts were issued to institutions in the United States, in Europe, and in Asia. The Breakthrough Starshot Advisory Committee, which included some of the most distinguished names in physics and engineering, identified the critical technical gaps and directed funding toward the teams best positioned to close them. The result, a decade after the announcement, is a landscape of incremental but genuine progress across nearly every major subsystem of the mission that would have seemed optimistic to predict in 2016. The sail materials problem is perhaps the area where progress has been most visibly exciting. The requirement for a sail a few hundred nanometers thick, reflective enough to catch laser light efficiently, robust enough to survive the acceleration phase without tearing, and light enough to stay within the mass budget of the mission is one of the most demanding materials science challenges ever articulated. But the field of two-dimensional materials that are literally one or a few atoms thick, has advanced with remarkable speed over the past decade. Graphene, the single-atom carbon sheet that won the 2010 Nobel Prize in Physics, has been joined by a growing family of related materials with different optical and mechanical properties. Hexagonal boron nitride, molybdenum disulfide, and various engineered heterostructures have been studied as sail candidates. Laboratory samples of materials approaching the required specifications have been produced and tested. The gap between what exists in a laboratory today and what the sail needs to be is real, but it is measurably smaller than it was 10 years ago. Laser physics has undergone its own quiet revolution that runs parallel to, and in some ways ahead of, the specific needs of Breakthrough Starshot. The development of high-power fiber lasers over the past 2 decades has transformed industrial manufacturing, materials processing, and scientific research. Fiber lasers are compact, efficient, and scalable in ways that older laser technologies were not. The technique of coherently combining multiple fiber laser outputs into a single beam, which is precisely what the Breakthrough Starshot array requires, has been demonstrated at increasing power levels in both military and civilian research programs. The Defense Advanced Research Projects Agency in the United States has invested heavily in laser beam combining technology for directed energy applications, and the engineering knowledge generated by those programs directly informs the design of the kind of array Breakthrough Starshot would need. The overlap between defense research and interstellar propulsion research in this area is not a coincidence. It is a convergence of requirements that is quietly accelerating progress on both fronts. Miniaturized electronics continue to advance along a trajectory that, if maintained even partially, will deliver chip-scale systems of extraordinary capability within the time frame relevant to Breakthrough Starshot. The smartphone industry alone has driven an almost incomprehensible amount of investment into making sensors, cameras, processors, and communication components smaller, lighter, and more power efficient with each passing year. The scientific community has been an active beneficiary of this investment, accessing commercial off-the-shelf components of increasing sophistication for CubeSat missions and other small spacecraft applications. CubeSats, satellites the size of a loaf of bread that now launch by the hundreds, have demonstrated that meaningful scientific instruments can be built at very small scales and operated successfully in the space environment. The Starship requires miniaturization well beyond current CubeSat technology, but the direction of travel is clear and the pace is measurable. Beyond the specific technologies of the mission, there is a broader shift happening in how the scientific and engineering communities think about small, fast, distributed space missions that is worth paying attention to. The old model of space exploration involved single, enormously expensive, one-of-a-kind spacecraft, each one handcrafted over a decade and carrying the weight of enormous expectations, precisely because replacement was not an option. The new model, emerging rapidly from the commercial space sector and from academic small satellite programs, involves constellations of smaller, cheaper, more standardized spacecraft where individual failures are tolerable because the mission is distributed across many units. This is exactly the philosophy that Breakthrough Starshot embeds in its fleet approach, launching hundreds or thousands of starships to ensure that the mission succeeds even if many individual chips do not survive. The cultural and engineering shift toward this distributed resilience model is happening independently of Breakthrough Starshot, and it creates a technological and institutional environment increasingly well suited to what the mission requires. What I find most striking when I look at the full picture of where the research stands is the contrast between the public perception of Breakthrough Starshot and the reality of what has been accomplished in the years since the announcement. In the public imagination, the project exists primarily as a bold and perhaps slightly impractical dream, a headline from a press conference a decade ago that was exciting for a moment and then receded into the background noise of ambitious scientific announcements. But in the laboratories where the actual work is happening, the picture is different. It is quieter, more technical, more granular, and in its own way more extraordinary than any press conference. It is the picture of real scientists solving real problems, piece by piece, year by year, without fanfare, because the problems are interesting and because the destination is worth reaching. The money was the signal that something serious was underway. The research that money has produced is the evidence that the signal was telling the truth. In the summer of 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory in New Mexico when the conversation turned, as it apparently did with some frequency among that particular group of minds, to the possibility of extraterrestrial life. The universe was known even then to be vast and old, containing hundreds of billions of stars in our galaxy alone, many of them older than our Sun. The mathematical probability that life had arisen elsewhere seemed, to many scientists, extremely high, and yet, as Fermi reportedly leaned across the table and asked with characteristic directness, "Where is everybody? If the universe is so large and so old, and if intelligent life arises with any reasonable frequency, then the galaxy should be full of civilizations, some of them millions of years more advanced than us, some of them capable of crossing interstellar distances, colonizing star systems, filling the cosmos with signals and structures and evidence of their existence. And yet we detect nothing. No radio transmissions, no signs of engineering, no evidence of any kind that anyone else is out there." That question, and the terrifying silence it points toward, became known as the Fermi paradox. There is a standard way of encountering the Fermi paradox, and it involves a kind of vertigo that arrives when you truly absorb what the silence means. Either life is so rare that we are essentially alone in the observable universe, an outcome that strains credulity given the sheer number of stars and planets involved, or something prevents intelligent civilizations from reaching the point of interstellar communication or travel, some filter, some barrier, some tendency towards self-destruction or stagnation that stops them before they can make their presence known. Or, and this possibility is the one that disturbs sleep most effectively, they are there, and they are silent for reasons we do not understand. Reasons that might tell us something very uncomfortable about what awaits a civilization that reaches our level of development. The Fermi paradox has no agreed resolution. It sits at the intersection of astronomy, biology, philosophy, and existential anxiety, and it has occupied some of the finest scientific minds of the past 70 years without producing a satisfying answer. But tonight I want to approach it from an angle that rarely gets discussed, because Breakthrough Starshot changes the geometry of this question in a way that I find genuinely startling when I follow it to its conclusion. We have spent decades asking why no one is signaling us, why no one has reached us, why the universe appears empty of other minds. We have pointed telescopes at the sky and listened for patterns in the noise and found nothing definitive. We have been, in the language of the paradox, the receivers waiting for a transmission that never comes. But what happens when we stop waiting and start transmitting? What happens when we become the civilization that sends a probe to another star? What does it mean for the Fermi paradox, and for our understanding of our own place in the cosmos, when humanity crosses the threshold from a species confined to its home system to a species that has reached, however briefly and minimally, into interstellar space? Here is the thing most people don't realize about what Breakthrough Starshot represents in this context. It is not just a scientific mission, it is a civilizational declaration. It is humanity saying, with hardware and mathematics and committed resources, that we are the kind of species that does not stay home, that we look at a 4.24 light-year gap and build a machine to cross it. Every other civilization in the galaxy that has ever asked the same question we're asking, whether anyone else is out there, face the same threshold we are now approaching, the moment of first interstellar reach, the transition from a planetary species to something larger. If that threshold is where most civilizations fail, for whatever reason, then crossing it is the most significant thing we will ever do. And if other civilizations have crossed it successfully, then we are about to join a category of beings that, by definition, the universe has produced before. There is a specific and interesting version of the Fermi paradox resolution called the dark forest hypothesis, which argues that the silence of the cosmos is not accidental but strategic. In a universe where resources are finite and the intentions of other civilizations are unknown, the rational behavior for any advanced species might be to remain hidden, to avoid broadcasting their existence, precisely because any civilization capable of receiving your signal is also, by definition, capable of sending something back that you might not want to receive. The universe is silent, in this view, not because it is empty, but because everyone is hiding. If this hypothesis has any truth to it, then Breakthrough Starshot carries a dimension of risk that deserves at least a moment of honest acknowledgement. We would be announcing ourselves, not with a radio signal, but with something more concrete, a physical object, a human artifact, arriving in another star system. Whatever is there, if anything is there, would know we exist, where we are, and that we are capable of interstellar reach. Most scientists consider the dark forest hypothesis more compelling as fiction than as astronomy, but the question it raises is not entirely without weight. Set aside the darker speculations, however, and what remains is something genuinely moving about the reversal of perspective that Breakthrough Starshot creates. For the entire history of the Fermi paradox as a scientific and philosophical question, we have been the ones listening. We have been the ones scanning the sky, hoping for a signal, wondering why the universe is quiet, feeling the particular loneliness of a species that suspects it might not be alone, but cannot find the evidence to confirm it. Breakthrough Starshot turns us into the signal. We become the probe crossing the void. We become the artifact arriving in a distant star system. We become, for the first time, the answer to someone else's Fermi paradox, if there is anyone at Proxima Centauri capable of asking it. The irony is almost too large to hold in your mind. We have spent decades wondering why no one has come to us, and now, perhaps within the lifetime of people alive today, we will be the ones who go. What this means for our self-understanding as a species is something I think we have barely begun to process. We have called ourselves many things across the span of human history. Homo sapiens, the thinking human, tool users, language users, culture builders. But interstellar species is a category of a different order entirely. It places us in a cosmic context rather than merely a terrestrial or even solar one. It suggests that the story of life on Earth, 4 billion years of chemistry and evolution and struggle and creativity, was not a local phenomenon without consequence for the universe at large. It was the universe developing, through us, the capacity to reach beyond its own home. The Fermi paradox asks where everyone is. Breakthrough Starshot is the beginning of humanity's answer. We are here, we are coming, and for the first time in the history of our civilization, those words are attached to an engineering plan. I want to tell you about a specific kind of human being, not a famous one, not someone whose name appears in history books or whose face appears on commemorative stamps. I want to tell you about the kind of person who spends their working life solving a problem they know, with mathematical certainty, they will never see resolved. The the kind of person who accepts, at the outset, that the reward for their deepest and most sustained effort will not come to them. It will come to strangers, people not yet born, people who will inherit the answer the way we inherit cathedrals, without any memory of the labour that raised the first stone. This kind of person exists. They have always existed. And they are in ways that I think deserve more reflection than we usually give them, among the most remarkable human beings our species has ever produced. The timeline of Breakthrough Starshot, followed honestly to its end, is a timeline that crosses generations in a way that very few human projects ever have. Consider what the numbers actually mean in human terms. The mission is currently in a research and development phase that most optimistic estimates place it somewhere between 20 and 30 years before a launch becomes feasible. That means a launch in the range of the 2040s or 2050s, assuming the engineering problems are solved on a reasonable schedule and the funding and political will remain in place. After launch, the fleet of starships travels for approximately 20 years. After arrival at Alpha Centauri, the data signal takes 4.24 years to return to Earth. The earliest plausible date for receiving the first images from another star system is therefore somewhere in the range of the 2080s or 2090s. A person who is 30 years old today, working on the Sail materials problem, or the laser phase locking challenge, or the miniaturized communication systems will be in their 80s or 90s, if they are alive at all, when that signal arrives. Most of the people doing the foundational work right now will not be there to see it land. This is not a new situation for humanity, and perhaps that is the most important thing to say about it. The great cathedrals of medieval Europe took generations to build. The workers who laid the foundations of Notre Dame de Paris in the 12th century did not live to see its towers completed. The architects who designed the dome of Florence's Santa Maria del Fiore in the early 15th century were solving structural problems that would not be tested until after their deaths, trusting that the mathematics was right, that the stone would hold, that the future would vindicate the effort. The scientists who developed the theoretical framework for quantum mechanics in the 1920s and 30s could not have imagined that their work would eventually make possible the transistor, the computer, the smartphone, and the miniaturized electronics that might one day power an interstellar probe. Every generation stands on the shoulders of people who could not see as far as the generation they were lifting, but Breakthrough Starshot makes this dynamic unusually explicit, unusually measurable, and unusually personal in a way that I think sets it apart from most long-horizon human projects. The cathedral builders knew their work would be used, would be inhabited, would be seen, even if not by them. The quantum physicists did not know what their equations would eventually enable. But the engineers working on Breakthrough Starshot know exactly what they are building toward. They can calculate to within a few years when the data will arrive. They can identify, at least in broad outline, what questions that data might answer. They're working toward a specific, defined outcome with a known timeline, and that timeline simply extends beyond the natural span of their lives. There is something uniquely clarifying about that situation. It removes any ambiguity about whether the work matters. It matters enormously. It simply does not matter in time for the people doing it. There is a question this raises that I find genuinely difficult to answer, and I want to sit with it rather than resolve it too quickly, because I think it deserves the discomfort. What motivates a person to do that? What psychological or moral or philosophical framework allows a human being, who, like all human beings, is finite and aware of that finitude, to invest their deepest creative and intellectual energy in a project whose culmination they will not witness? The cynical answer is that the work itself is interesting enough, that the problem is its own reward regardless of when the solution is confirmed, and there is truth in that. The science of laser-phased arrays and graphene sail materials and miniaturized space instruments is genuinely fascinating in its own right. But I do not think that is the whole story. I think something else is operating in the people who commit to this work, something that has to do with a conception of human identity that extends beyond the individual and into the collective. We are, in some deep and important sense, not just individuals. We are also participants in a civilization that extends backward in time through every human generation that preceded us and forward in time through every generation that will follow. The knowledge we have inherited, the technologies we use every day, the languages we think in, the scientific frameworks within which we understand the universe. None of these were created by us. They were created for us, by people who had no way of knowing we would exist, no way of imagining our specific needs and questions and circumstances, but who understood that their work belonged to the future as much as to the present. Working on Breakthrough Starshot is, in this sense, simply the continuation of something that every scientist, every engineer, every artist, every thinker who has ever contributed something lasting to the human project has always done. It is working for people you will never meet, because those people are real, their curiosity is real, and the answer you are building toward is real, even if the timeline keeps you from being there when it arrives. There will be a morning, somewhere between the 2080s and the end of this century, when a signal arrives from Alpha Centauri. It will be faint, a whisper of laser light attenuated across 4.24 light-years of interstellar space, detectable only by instruments designed specifically to find it. The people who receive that signal will know in the moment of reception that they are holding something that was sent by machines designed by human hands now long still, carrying data gathered by instruments that crossed more empty space than any object in human history, returning from a destination that our civilization spent thousands of years dreaming about and decades actually planning to reach. They will feel, in that moment, the presence of the generation that built the thing they are receiving from, the generation that solved the sail problem and the laser problem and the chip problem and never got to know if it worked, the generation that planted the tree, and on that morning, across whatever the world looks like by then, something that began in a desert laboratory and a university materials science department and a laser physics research group will complete its journey. Not for the people who started it, for the people who inherited it. Which is, in the end, exactly as it should be. It is a fair question, and it deserves a fair answer, which means it deserves an honest one, without the inflation that tends to accompany ambitious scientific announcements, and without the reflexive skepticism that tends to follow them once the initial excitement fades. So let me try to give you that honest answer, because I think you have earned it by coming this far through the story tonight. The question is not whether the physics works. We have established that it does. The question is not whether the engineering is theoretically achievable. We have established that it is, at least in principle, and that measurable progress is being made on the hardest problems. The real question, the one that determines whether starships actually leave Earth in the 2040s or whether Breakthrough Starshot joins the long list of grand ideas that inspired a generation and then quietly faded, is whether the full constellation of requirements, technical, financial, political, and institutional, can be assembled and sustained across the decades required to bring this mission to launch. That is a harder question, and the honest answer is probably yes, but not easily, and not without deliberate effort on a civilizational scale. Let's start with the technical obstacles that remain genuinely unsolved, because naming them clearly is more useful than either dismissing them or dramatizing them. The phased laser array is the single largest unresolved engineering challenge in the mission. Combining millions of individual laser units into a coherent beam of 100 gigawatts, maintaining phase lock across a kilometre-wide installation, tracking an accelerating sail through the atmosphere with sub-millimetre precision, and doing all of this without destroying the installation itself in the process, represents an engineering achievement that has no direct precedent. The components are not impossible, but their integration at the required scale has never been attempted, and the path from current laboratory demonstrations to a functional full-scale array involves engineering steps that will each require years of focused work and significant investment. The same is true, though to a lesser degree, for the sail materials. The Starship electronics are closest to readiness. The communication and power systems are in the middle. The array is the long pole in the tent, and everyone working on the project knows it. The funding picture is more nuanced than it might appear from the outside. $100 million is a significant sum for a scientific research initiative, and it has produced genuine results. But $100 million is not the budget for building the mission. It is the budget for the research and development phase, for identifying and beginning to close the technical gaps. The actual construction of the laser array, the manufacture of the starships at scale, the ground infrastructure for receiving the signal, and the operational costs of the mission over its multi-decade lifespan will require resources measured in billions, not hundreds of millions. By some estimates, the full mission cost could approach $10 billion or more. That is comparable to flagship NASA missions like the James Webb Space Telescope, which cost approximately $10 billion and took over 2 decades to complete. It is not an unachievable number for a civilization that routinely spends comparable sums on much less historically significant endeavours, but it requires either a sustained commitment from a private funder of extraordinary wealth and patience, a multinational governmental collaboration of the kind that produced the International Space Station, or some combination of the two that has not yet been formally organised. The geopolitical dimension of the laser array deserves particular attention because it is one of the aspects of the mission that receives the least discussion in popular accounts, and is in some ways the most practically challenging. A ground-based laser installation delivering 100 gigawatts of coherent directed energy is, as I mentioned earlier, a dual-use technology of obvious military significance. No single nation is likely to permit another nation to build and operate such an installation on its soil without extensive negotiation, treaty frameworks, and international oversight mechanisms. The ideal scenario, which most of the scientists involved acknowledge as both desirable and difficult, is an international consortium operating the array under a governance structure similar to CERN, the European Particle Physics Laboratory, which is jointly funded and governed by 23 member states and has managed to sustain multi-decade scientific programs through changes of government, economic cycles, and shifting political priorities. Building that kind of institution for Breakthrough Starshot in the current geopolitical environment is not a physics problem or an engineering problem. It is a diplomacy problem of considerable complexity. And yet, when I talk to the researchers involved in this work or read their papers and public statements, what I find is not the brittle optimism of people overselling a project they privately doubt. What I find is something more measured and in its own way more convincing. It is the quiet confidence of people who have looked carefully at the hardest problems and concluded that the problems are hard but not impossible, that the trajectory of the relevant technologies is favourable, and that the case for doing this is strong enough to justify the difficulty. Avi Loeb, the Harvard astronomer who served as chair of the Breakthrough Starshot Advisory Committee, has written and spoken extensively about the project with a combination of scientific rigour and genuine enthusiasm that reflects a real assessment rather than a promotional posture. The engineers working on laser combining and sail materials at universities around the world are not spending their careers on a fantasy. They are solving real problems that are getting incrementally more solved with each passing year. There is also a factor that tends to get underweighted in assessments of long-horizon technology projects, and it is the factor of unexpected acceleration. The history of technology is littered with examples of capabilities that advance far faster than the most optimistic experts predicted, once the right combination of economic incentive, competitive pressure, and enabling technology converged. Solar power was supposed to take a century to become cost competitive with fossil fuels. It took 30 years. Genomic sequencing was projected to remain expensive for decades. The cost collapsed in less than 10 years. Reusable rocket boosters were considered impractical by much of the aerospace establishment as recently as 15 years ago. SpaceX made them routine. Any of several enabling technologies for Breakthrough Starshot, laser efficiency, materials science, miniaturized electronics, could follow a similar trajectory of unexpected acceleration. The engineering roadmap that looks like a 30-year journey at current rates of progress could compress dramatically if any of its key components advance faster than expected. So are we actually going to do this? My honest answer, having followed the full arc of the story tonight, is this. The physics says yes. The engineering says yes with difficulty and time. The money says probably if the will is there. The geopolitics says possibly, with sustained effort and institutional creativity. The history of human technological ambition says that when a civilization identifies something as both possible and important, it tends to find a way, eventually, even when the path is long and the obstacles are real. Breakthrough Starshot is possible, it is important, it is further along than most people know. The remaining question is not really a scientific or engineering question at all. It is a question about what kind of civilization we choose to be. Whether we are the kind of species that looks at the nearest star and builds the machine to reach it, or the kind that calculates the difficulty and decides to wait for a better moment. I think we both know which kind we are. The dream is 4.24 light-years old and it has never been closer to becoming real. There is a thought I want to leave you with tonight, before you close your eyes and let the darkness take you somewhere quieter than the cosmos we have been travelling through together. It is not a complicated thought. In fact, it is one of the simplest thoughts available to a human being. But simplicity, I have found, is often where the deepest things live. Underneath all the numbers and the engineering and the light years and the laser arrays, the thought is this. Every atom in your body was forged inside a star. The carbon that forms the backbone of every molecule in every cell of you was synthesized in the nuclear furnace of a stellar core, billions of years before the Earth existed, and scattered into space when that star died. The iron in your blood was produced in a supernova explosion so violent that it briefly outshone an entire galaxy. The calcium in your bones, the oxygen you're breathing right now in the quiet of wherever you are lying or sitting as you listen to this, all of it came from stars. You're not looking at the stars from the outside, you are made of them. You are the universe shaped by 4 billion years of chemistry and evolution into something capable of looking back at itself and asking, "Can we go home?" We have covered a vast amount of ground tonight, and I want to draw it together gently before we part, the way a long journey deserves a moment of stillness before the traveller finally rests. We began with the oldest dream our species has ever had, the longing to cross the dark between the lights, the pull toward the stars that has lived in human consciousness for as long as we have been capable of consciousness at all. We looked honestly at the distance, at what 4.24 light years actually means when you translate it into miles and years and human lifetimes. We stood with Voyager, our most distant ambassador, and felt the weight of 73,000 years. We sat with the announcement of Breakthrough Starshot, a gram-scale chip on a laser-push sail aimed at another star, and felt something shift in the way the future looks. We walked through the physics of light as an engine, through the extraordinary miniaturization of the starship, through the almost incomprehensible scale of the laser array that would push it free. We faced the gauntlet of interstellar space honestly, the dust and the radiation and the silence and the constraints of a flyby that lasts minutes after a journey of 20 years. We visited Proxima b, the world that might be waiting, and felt the full existential weight of not knowing what is there. We thought about the generation that will build this and not live to see the answer, and found in that thought not sadness but something closer to reverence. And now we are here, at the end, in the particular quiet that long contemplation of large things tends to produce. I want to say something about what all of this means, not scientifically, not technically, but in the way that matters most when it is late, and the world is dark and you're lying somewhere with your eyes either closed or about to close. What it means is that we are not small in the way we sometimes feel small. The smallness is real, in the sense that the numbers are real, in the sense that 4.24 light years is genuinely, staggeringly far, and that we are genuinely measurably tiny against that distance. But smallness of scale is not the same as smallness of significance. A universe that had been producing stars and planets and chemistry for 13.8 billion years eventually produced something that could notice it was doing so. That is not a small thing. That is, as far as we know, the most extraordinary thing the universe has ever accomplished. And we are it. We are the noticing. We are the universe's way of looking at itself and saying, "I wonder what is over there." Breakthrough Starshot, when I step back from all the engineering and hold the full arc of the idea in my mind, is not really about a gram-scale chip on a laser sail. It is not really about 20% of the speed of light or phased laser arrays or graphene sails, or the habitable zone of a red dwarf star. Those things are real and important, and I have tried to honour them with the attention they deserve tonight. But underneath all of them, at the level where science and philosophy meet, Breakthrough Starshot is about a species deciding to become something larger than it has ever been. It is about 4 billion years of evolution producing a creature that looks at the void and chooses, deliberately and with full knowledge of the cost, to cross it. Not because there is profit in it, or because survival demands it, or because some authority commands it, but because the question of what is out there is the most important question we have ever asked, and because we have finally, perhaps, found a way to begin answering it. The stars were always waiting. That is the thing I keep coming back to, in the quiet after all the numbers have settled. They were there before the Earth existed. They were there when the first living cells formed in warm, shallow water and began the long work of becoming us. They were there when our ancestors looked up from African savannas and felt something they could not name. They were there when the first human being painted a star on a cave wall, or named a constellation, or told a child a story about what the lights in the sky might be. They have been patient in the way that only things measured in billions of years can be patient. They did not need us to notice them. They simply were, and we eventually could not help but notice, could not help but wonder, could not help but reach. Thank you for spending this time with me tonight. Thank you for following this story all the way to its edge, where the known gives way to the possible, and the possible gives way to the not yet. If this journey has moved something in you, if it has left you with a sense of the immensity and the strangeness, and the sheer unlikely beauty of the universe we inhabit, then I hope you will take a second to like this or subscribe. It is a small thing, a gesture no larger than a grain of interstellar dust, but it helps this channel reach more curious minds, more nighttime wanderers, more people who feel that pull toward the dark and the distant and the unknown. And that, I think, is worth something. Now let the numbers go. Let the light years dissolve. Let the laser arrays and the gram-scale chips and the gauntlets and the flybys all fade back into the dark where they live. What remains, when everything else is quiet, is this. Somewhere out there, 4.24 light years from where you are lying right now, a small red star is shining. Around it, a world is turning. And on this world, at this moment, we do not know what is happening. We do not know if there is wind or water or silence or something else entirely that we have no name for. We only know it is there. We only know we are here. And we are finally, after all this time, building the bridge between the two. Sleep well tonight. And the next time you step outside and look up at the night sky and find that warm point of light near the Southern Cross, just remember, we're going there, the stars were always waiting, and we are finally at last on our way. Good night.